Yeah, so last night, while I was having an existential crisis in the Carl's Jr., I was able to work on this for a long time, and so I lied a little bit, but it's okay. I'm going to be doing an example, proving my first assertion, whatnot, through the Klein bottle, through the example of the Klein bottle. But what I really want to talk about, and what is really fascinating, and what really started to fascinate me as I studied this, was this idea of group presentations. And what happens when we take a particular group presentation and we add some other relation to it. In particular, what happens to the group's Cayley graph. So immediately you want to be like, you would hope it's subgraph-ish. And if you're hoping it's subgraph-ish, you're right, it is subgraph-ish. It's a quasi-subgraph in a sense. I mean, you immediately know, because if that were true, then everything would be a subgraph of a free group, which we know it's not. But there's a very natural sense in which something with a particular Cayley graph relates to another group presentation with that relation and one more. That's very interesting. Now, the usefulness of this particular idea comes in constructing certain Cayley graphs. I haven't been convinced yet that there will ever be a case where what we're about to discover about the relationship between these two Cayley graphs will make it actually easier to construct the Cayley graph simply by imagining the simpler one. But there is a case where our intuition will fail us, and once we imagine it in this way, we'll begin to understand exactly why the Cayley graph of the infinite dihedral group looks the way it does. And it's because the infinite dihedral group is related to the most basic group whose fundamental domain is the Klein bottle. So let's deal with this. So like he did, we have one orbit space here. This is the torus, like we all know and love and have become very acquainted with over the course of the 2 weeks. And this is the orbit space of the group with presentation A, B, A, B, A inverse. B inverse, which is, of course, just Z cross Z. So, how do we make the Klein bottle? That's the question. What is the actual object we're looking at? That would be a wonderful place to start. So in order to figure out exactly what the Klein bottle looks like, we start off with that idea of a Mobius strip. And we can, you know what, let's not start off with the idea of the Mobius strip. That's just going to overcomplicate things. So here we go. When we get these together and we make this into a cylinder, when we do the torus, we're lucky because these arrows on top are pointing in the same direction. But now, when we make the cylinder, the arrows are pointing in the opposite direction. So what we need to do is we need to connect these two edges, but we need to do it so that the arrows are pointing in the same direction. Obviously, that's going to be incredibly difficult to do in just three-dimensional space, so we have to fold it through four-dimensional space. And since I cannot draw that, we do have a simple representation. So what we need to do is we need to get these arrows pointing in the same direction, these orbits moving in the same direction. So what I'm going to do is I'm going to drag this side right here. I'm going to move it inside and line it up like that. And this is a very basic depiction of the Klein bottle. What you can imagine is that this thing is actually moving inside of the cylinder and lining up. And if we fold through four-dimensional space, there are no intersections happening. Since we can't do that, we're going to have to use our imaginations. So the amazing thing about the Mobius strip, two-dimensional object, one side. That's cool. The amazing thing about the Klein bottle, three-dimensional object, one surface. And it looks as though it should have two, and it looks as though it has space, but if you pour water in it, all the water is just going to fall on the floor. And as soon as you look at it, your intuition says there's an inside to this thing, but if you follow it with your chalk, it's going to sit on the outside. So let's say we're sitting on the outside right now, and when we get right here, it's going to lip over into the inside of the bottle. And so when we get back to this point, we're going to be on the opposite side of the same surface. So we continue moving through, and when we come back up, we lift back onto the outside of the bottle. And that's easier to see if we have a better depiction, which is why
I have one. But
yes,
go ahead.
that'd be wonderful. Okay, well, you're pulling that up right quick. You got it?
Yeah.
There you go.
I dropped it.
No problem. That's my favorite one. Thank you. Yeah. Okay. So this is the picture, and this is where you can see really intuit that this only has one surface. It only has one side. If you follow it with your finger, you end up going inside of the bottle, and when you come through here, you're sitting on the inside of the surface. You're sitting on the inside of the surface, and when you loop back around, now you're walking on the outside of the surface. Now, obviously, we can't do this unless we're moving through the surface in a sense, but you can fold it through four-dimensional space in such a way that it does not intersect with itself. Thank you very much. Okay, so what is the most basic group that we're dealing with? In the same way that this can be represented by AB, A inverse, B inverse, how are we supposed to think about this object? And thankfully, we have a very natural, very easy way to figure out what really basic group that's the fundamental domain of, and that is by the disk method, which we did with the torts, where what you do is you take the Klein bottle, and you imagine that we have a disk on the inside of it. Okay, so now then we're going to stitch the disk to the edge of the edges, and we're going to count as we do so. And what we get here is we get A, B inverse, A, I'm sorry, A will, and it ends up being A inverse and then B inverse again, but another way to say that is A, B, and then A, B, A inverse, B. Okay, this is a very hard Cayley graph to draw. Thankfully, Dr. Abrams came to my rescue and taught me a very simple way that we can imagine these orbit spaces and turn them into Cayley graphs. And as we'll see, it works out quite well. So all we're going to do, that's it. All we're going to do is we are going to, here, I'll grab this piece. We are going to tile the plane with these guys, okay? And then we'll begin to understand what exactly this group is doing. So here we go. It is going to be my hardest picture I draw all day, I think. So let's try this. I'm going to get a grid like this. Make it nice and big so that we can imagine it. And it's going off to infinity in all directions. Okay, now let's call this E right here. And these A's are all pointing in the same direction. The B's are pointing in alternating directions on the plane. Okay, so let's check. I mean, it's pretty obvious, but let's check. Start at a point. Let's go A, B, A inverse, B. Clearly, that's going to return us back to the same point. How to imagine this group? I was trying to figure out how to describe it. I wanted to call it twisted plane, but the most basic and most fundamental way to understand what is actually happening here, I did all the calculations out, and the relations we end up getting is A, B equal to B inverse A, and I mean similarly BA is equal to A B inverse, and then BA inverse is equal to A inverse B inverse, and B inverse A inverse is equal to A inverse. So B commutes, but when it commutes with A or A inverse, it switches its it becomes its own inverse at that point. So that makes sense. If we perform A first and then we perform B, to get to that same point, if we switch it, we're going to have to move in the inverse direction of B at that point and then move up in the direction of A. So there is an intuitive understanding of this. I still don't know what to call it. I'm going to call it the twisted plane because that's what I'm kind of seeing. You're twisting it at each point, and every time you turn around, you move up a spot, you're heading in the opposite direction.
So you're saying whenever you have any kind of A, whether inverse, and any kind of B, whether it's B or B inverse, you can swap them if you switch the sign of
Mhm.
B. Is that what's happening?
Yep. Yeah, so and I checked, I did all the algebra out, and that is that you can derive all that from AB, A inverse B. So B commutes with A can stay the same sign, but B has to switch signs when it does so. And so yeah, so I mean just one easy example. Let's do one easy example. BAB. Well, that should be equal to A. Crossing our fingers. Well, we go BAB, and that is in fact the same thing as just going up A. So, this is looking like it's pretty true. Now then, we constructed the Cayley graph of this thing whose fundamental domain is the Klein bottle. And now I'm going to start talking about dihedral groups. I'm going to just switch gears completely here. And what we're going to see is that the dihedral groups are actually this group presentation plus some more relations. It's not obvious at first though. So here we go, group participation. Are you ready? DM. This is a group of rotations on a particular n-gun. We've got A, B, and who can give me the relations? Who I didn't talk to already.
Wait, is it an M-gon?
M-gon. Let's call A's flips and B's rotations.
Okay,
So-
so we used to call this D2M, right?
Right.
Oh, sorry.
M or-
Okay. We'll call it 2M.
So B to the M.
B to the M. Great. Thank you for choosing B for that.
And it's
A squared. Awesome. We're missing one. And this one, or D3, or D6, excuse me. Let's draw D6. And we'll see the AB right quick. And I'm needed for later anyway, so this will all work out. And we have a smaller triangle on the inside. Arrows here. Arrows moving the other direction here. First of all, this does not look to be a subgraph of this in any way, shape, or form, but we will be figuring that out later. So let's look at this. We've got A, B, and as we will always see, if we go to any dihedral group, there's going to be this for loop in it, which is commutes with itself through performing A, B. We lucked out though. We're very lucky people, because since A squared is one of our relations, A ends up being the exact same thing as A inverse. So we can just call it A inverse. When we call it A inverse, we now see that this thing is what I'm going to call the bottle group from now on. We're just going to call that the bottle group. Is the bottle. Great question. Still going to ignore that for 1 second though. First, we're going to see if we can figure out D infinity. Okay? So, D2 infinity. We're going to figure out D2 infinity. So we got an m-gon inside of an m-gon, right? That's what D2m is. That's what the Cayley graph is always going to be. So as we approach infinity, we should have an infinity-gon inside of an infinity-gon. Or in other words, we should have, our intuition sort of tells us that we're going to in some way approach a circle within another circle. There's this mapping from the edge of the circle to the inside of the circle. And that this is pointing in one direction and that this is pointing in the opposite direction. If this were true, and it would be awesome if it was, since these are kind of related, then what we could do is we could just cut it open. And if we cut this open and unfold it, well, look at that. We get a shape that just happens to look like... one second. Those can both go up in these opposite directions. We get a shape that looks like, you know, the wine bottle over here. So that would be pretty cool. But it ends up that this is our intuition fails us in this case, and that this is not an accurate representation. So the group presentation of D infinity at that point would be A, B, such that A squared, since M has gone to infinity, it just drops out, and we have A, B, A inverse B. Okay? So, what would performing B on imagine this as a continuous space. If we perform A on this, it clearly goes to the other side and comes back, it flips, and that's okay. But where does it go if we do B? Where does it move? If we perform B on our object, where does our point move?
Nowhere?
Just chills, because if it moves any finite distance, then there should be a finite number of rotations which carries it back to itself, and that's impossible because we are in the infinity. So this picture ends up going against our intuition and being wrong because B does not act on the space whatsoever. So we have to figure out what is in fact a D-infinity. I'm still convinced it would be easier to just work it out normally, but instead we're going to figure it out by looking at this thing's Cayley graph. Yeah?
Could it be like an irrational multiple of 2 pi b? Because we talked about how rotations, if it's an irrational multiple, will never come back to itself. Because it's, if it did have a finite order, then it would have to be a rational multiple of 2 pi. Idea?
But
Well, I mean, I have a couple problems with that.
yeah, I think that stops working. Like if we're talking about the symmetries of an infinity gone, then we would, I think those are different creatures.
And we're also still in countable land, which is weird, which is why those circles are weird, because we've taken m to infinity, but it's still not uncountable, so choosing an irrational number isn't even an option in this case. Not to mention, when we were talking about the rotations earlier, there seemed to be more than one problem with that, but I'm not mathy enough to figure that one out. So,
Right, so that isn't one of the issues that came up, that isn't a geometric action.
yeah, that's what it was. Yeah, that wasn't a geometric action. Okay, great. So we've got this graph, and we see that our D-infinity's presentation.
Wait. Don't erase. Go over there instead.
Sorry. We see that D-infinity's presentation is very similar to our bottle presentation. So how to think of this? Great. Let's walk over here. ABA inverse is preserved. We've thrown in another one, A squared. So starting from E, every single time we try and move up any more, we're going to be carried back to ourselves. Keep trying to escape, but we can't escape, and we won't. So, this suggests that perhaps the infinity's Cayley graph looks something like this. Which is all well and good, but there's a problem. This looks nothing like this. Not yet, at least it doesn't. We can make it look like it, and that's when we begin to see the power of performing these actions. So here we go. This is in fact a Cayley graph of D infinity. Question? Okay. So now let's look at E2M and see if we can somehow make sense of it, and then we'll begin to see the relationship between Cayley graph and its relation. Okay, so what I'm going to first do is I'm going to take these objects and I'm going to turn them into straight lines. Okay, so this thing is the same graph as this guy. 1, 2, middle. Got a third point here, third point there, and okay? So if we start from E here, when we perform AB, right? Go A, B, yes, B, A, A, and then B. That's going to carry us back to our
Are
same
you supposed
spot.
to look on their side there, Jack, or is it?
Oh, yeah, thanks. Oh, wait, yeah. Appreciate that. Okay, so this is another representation of this thing. In fact, we can do that to any Imgon dihedral Cayley graph. We can write it in this manner. So now what I'm going to do is I'm going to grab this thing and I'm going to twist it. Okay, and when I twist it, we're going to imagine us going over here right quick. So when I twist it out all the loops, then what I get is obviously this thing. And I'll just draw it without arrows for right now, but and these arrows are pointing in opposite directions. And we can imagine this as looping back on itself. Sorry. Great. And now this is beginning to look like subgraphish. It's not a subgraph because this has loops in it that this thing does not have, but it's subgraphish. So what is happening when we are adding relations to a graph to get the next one's Cayley graph? Well, we're pinching things shut, and that's the best way to think of this. We're taking things in A, B, A inverse B that were not equal to E before, and we're making loops out of them. So here we imagine to get B infinity, when we insert the relation A squared, and what we're doing is we're folding it all on top of itself into almost a, a cylinder shape, so that A squared is preserved. And then, when we do another dihedral group, after folding A squared in on itself, if B cubed becomes another relation, you imagine grabbing that graph again and folding it in the other direction, and that's how you will produce any D sub m, which is produced by B, M, and A squared. In fact, if we have some B to the M, A to the N, A, B, A inverse B, we're going to get an n by n square of this grid, is what's going to end up happening, where the n's loop back in on themselves. So, to make this a little more tractable and to get one more sexy example, oh wait, hold up. Do I want to do that? How much time do I have?
Start a little late, but it's 11, so you should.
Okay. So hey, fun fact, I'll just say this right quick and let y'all mess with it, but it works out in a very beautiful way. If I were not stuck in San Francisco at 4 a.m. in the morning yesterday, I would have come back and I would have had somebody write a computer program that would show you something absolutely gorgeous, which is the fact that, let's be honest, D6 equal to A, B, A squared, B cubed, A, B, A inverse B. It's the bastard child of one of our two presentations, AB, A squared, B cubed, which we're so comfortable with at this point, and AB, AB, A inverse B. These two Cayley graphs look nothing like one another, but there's a beautiful way you can fold this graph up onto itself and then pull it out and get the twisted plane, as I'm calling it, the bottle Cayley graph. And it really is gorgeous. I wish I could show it to you, but I'm going to skip that for the much more tractable, much more useful example of the free group. And this is where you see pinching, and pinching all of a sudden, like, hopefully a light bulb will come on for someone. So here we go. We got the free group's Cayley graph. How far do I have to go out? I have to go out this far. Okay, so now then, this is simply AB with no relations on it. So what I'm going to do is I'm going to add the relation. I might need to go out one more, and if I do, forgive me. AB, A inverse, B inverse. So I'm going to add that relation. Okay, this can turn into four different things. It can become A inverse AB, B inverse A inverse, BA, BA, B inverse A inverse. Sorry about that. And that's just gotten by the fact that these commute and their inverses, taking the inverses of the commutations will get us all that. So let's start from a point and let's do it. I didn't go out far enough. I have to go one more, unfortunately. I didn't think I did. Okay, here we go. Yeah. Okay, I'll just stop right here for right now. Okay, so here we go. Call this A, call this B. Okay, here we go. So going A, B, A, or, yeah, no, sorry, A, B, yeah, going up. So here you go. We got A, B,
Versus, right? A, B,
Yeah,
whatever you do.
oh, sorry, thank you, that's why I wasn't looking right, appreciate that. Okay, so we go A, B, that's why I wanted to go in this direction, A inverse, B inverse, and you pinch that down to the origin. Let's do it again. B inverse, A inverse, and then we're going to go B and then A. We're going to pinch that down to the origin. So what are we getting? We're getting boxes of size 4. Around each point, there are going to be 4 such boxes, one corresponding to each of these, okay? And the direction of these boxes, if we look at them, are in fact the direction that we want. Or sorry, these are heading in the opposite direction because we had to move in inverses to get there. And that is Z cross Z, which is produced from the free group by pinching these points down into loops. So, is it subgraph? Ish. Quasi. We are doing quasi-Cayley subgraphs because this whole field is based on sort of kind of things, apparently. Anyway, thank you very much. If you want to see mathematics in the wild, one group mate with another, just ask me and I'll show you their beautiful child. It's actually kind of cool. So, thank you very much. I appreciate it.